Okay, so let's get started on the second question, which involves filling in the blanks. Now, the blanks could be the end product, it could be the starting reagents, it could be the reactants. It doesn't matter. As long as you can analyze a reaction the right way, you should be able to get anything out of it. So the first reaction we have over here involves a hydroxyl group, a secondary hydroxyl, and treating it with chromic acid, H2SO4, and H2O. So this is an oxidation reaction. And what you're doing here is you're converting your hydroxyl group, you're oxidizing it into a ketone. It's a ketone because this carbon here that'll be part of the double bond is flanked or is connected to two R groups. So how would you draw that out? You just draw your ring as you normally would, and then your hydroxyl is immediately converted to a ketone. So you lose the hydrogen and you form a double bond between oxygen and the carbon. In the second question, we're asked to figure out the reagent necessary to convert our aldehyde into a hydroxyl. Again, you can ask yourself what's changed between the two, right? It's something I always ask you guys to do. Well, first of all, you're obviously reducing the compound. We are adding hydrogens to it, and you're also adding a CH3 group, right? Here we only have one R group projecting off of our carbonyl. Here you got two R groups, R and R prime. So obviously you've added carbons, and how would you go about that? You have an aldehyde. You don't need to make an alkyne. So you can use a Grignard reaction where you add on carbons that matches the second R group projecting off of the carbon that was once your carbonyl. So CH3 MgBr because we're adding the CH3, and an H2O step, a proton source for when you form your alkoxide anion. And if you don't know what that is, you might want to reference your mechanism. Next, we're taking our alkyne, treating it with 9-BBN, H2O2, and NaOH in the second step. Now, you should remember this reagent, especially since we're at the University of Kentucky. And importantly in this reaction is it converts an alkyne into an aldehyde, specifically if it's a terminal alkyne. So you just write out the number of carbons associated with this compound and then draw out the number of carbons, so 1, 2, and 3. And from there you would make an aldehyde projection. Carbon 3 is where you would be adding that aldehyde to, because that's the least substituted region. This is sort of the anti-Markovnikov addition of a hydroxyl group that spontaneously tautomerizes into a ketone or aldehyde. In this case, because the hydroxyl was placed on the least substituted, its spontaneous tautomer form would be the hydroxyl, or rather the aldehyde. Now, you could have used either this information here to the left or the information to the right to solve the problem. If you use lithium aluminum hydride and water, you get this primary alcohol out of it, and this compound is in agreement with the reaction. So you could have used two different data points to analyze this reaction and get the right product. I primarily use this because you guys would have been more familiar, but if you ever think that you may be wrong, you can always use the next step of the reaction to either confirm or deny whatever you have drawn as being the product. And here's an interesting one. So we're going to compare we're going to figure out what happens to this reactant we don't know of when it's treated with SOCl2 and pyridine to form this compound. Well, it's important to ask yourself, what does SOCl2 do? And what kind of functional group does it react with? Well, if you ask yourself that and answer that SOCl2 functions to replace a hydroxyl group with a chlorine, and this occurs in an SN2 fashion. So what that means is you need to keep in mind there is an inversion of stereochemistry at the center which is being replaced or substituted. And once upon a time, at the center where the chlorine exists, there was an OH group present. So you scan your product and you find your chlorine is present right over there. So you would draw out the same backbone you had before. Forgive my drawings, this tablet is very interesting and difficult to use. There's a CH3 projection and an iodine projection. That iodine is not substituted in this reaction because that center over there is an sp3 center, and it's also tertiary, so it's not going to be attacked by an SN2 reaction. However, we know that this carbon here had to bear a hydroxyl group because that's where SOCl2 has done its magic, but it was on a wedge, not on a dash, because this chlorine is now on a dash. That means there had to be an inversion of stereochemistry, and this is the final product that you'd get out of it.